is dynamic data flow. So that we'll be seeing it today. So dynamic data flows. Okay. So yesterday we could not able to see some examples for synchronous data flow. So today we will see that also in Ptolemy directly. I will just show you, and the DDF also we will see some things. So we have few slides now to explain what is DDF and in what way they is differing SDF. Then later on we will see the real example in Ptolemy 2. Okay. So dynamic data flow, as the name says it is dynamic. So already we have discussed something on static data flow. So I'll merge both the presentation in one slide so that you don't have to refer everything together, because that's I already got ready in PowerPoint. This in some other software. Anyway, so it is flexible than an SDF. So dynamic data flow is flexible than an SDF. We will see how it is flexible. In SDF, we have seen the actors can produce and the actors can consume the fixed number of tokens. The tokens will be generated. I'll tell you with an example SDF. So we have a box A and we have a box B. So box A is an actor A. The actor A generates some tokens or produces some tokens, which will be consumed by B. If and only if the condition will be QA into QA into M equal to QB into N. That means the number of times the actor is fired and generates token, it has to be consumed by the actor B, in which it also fires the number of times. So that's what the condition we have said. Okay, but in a synchronous DF, that is in synchronous data flow, static data flow, the actors can produce and consume fixed number of tokens, but whereas in DDF we can have varying number of tokens in each firing. So the DDF can able to have varying number of tokens during each firing. So every time when it execute, it might be having a varied number of tokens. Okay. So one good example is a file download. So you might have seen there are two examples. Let me tell you that. Let's say I want to hear a song in Amazon Prime Music or Spotify. Let's say I want to listen to a song. Okay. Now, two options are there. One option is I download the song to my computer or to my phone. Then I open the song and then I listen to it. That is one method. Another method is directly through streaming, I listen to the song. So there are two options. One is streaming, another is downloading and listening offline. Okay. And streaming also nowadays, what do? Is they store locally within the app itself, and it will be stored locally. And even without network connection, you can listen to the song. So two options are there. One is through streaming, another is downloads. So when you, let's say if you download that song, let's say the song is around 20 MB, for example. Let's say the song is around 20 MB. Okay, so the song 20 MB, what happens is when I download, the download speed it shows like this. So the download speed shows like this. So here this could be around 100 kbps, for example. So this is around 100 kbps. So this is the download. So at this time, let's say point or 5.7 seconds, the entire song is downloaded. So up to 5.5 seconds, you can see the waveform. The waveform is completely cluttered. That means it is sometime there is 100 kbps reaching, sometime 150 kbps, again come down, again 170, 60 kbps. Then finally it reaches within some 5.7 seconds, the song is downloaded. So this is one option. So downloading a song. Okay. Now the other way around is I listen through the streaming. I didn't download, but rather than I stream it using Spotify. Okay. Now it's like this. What it says is 320 kbps. 320 kbps. Okay. So let's say this is 320 kbps. And somewhere here I have 192 kbps. What happens? High quality song, when you want to listen, I go for 320 kbps. Low quality song, I can go for 192 kbps. Still more down, 128 kbps. Still more, 94 kbps. So all the streaming app, they have an option, use less data. So there's an option called as use less data. In that option, when you go for whether it's Spotify or Prime Music, it has an option. When you go for it, so the song will be streamed at a lower kilobit per second rate. So 192 kbps means 192 kilobits per second. So per second 192 kilobits will move. So the quality of the song is slightly less when compared to 320 kbps. So now 20 MB I have downloaded. So when 192 kbps is there, so it will be coming around 11 MB for example. In 320 kbps it comes around 20 MB. Still more, I don't have a 3G 4G connection, I have a 2G connection. Still if you want to listen to the song, then the song can be scaled down to 64 kbps or 128 kbps. Okay, so that these two difference. Now why I am coming here is the streaming application usually handled by synchronous data flow, because every time the song is fired, the data bit rate doesn't change. 192 kbps is 192 kbps. That is synchronous data flow. That is static data flow. But uh, for example, the dynamic data flow, it is like a file download. So for one firing, the 60 kbps was there. I mean, the download speed is 60 kilobits per second. For the next firing, it might have reached 150. Then again, it comes to 100, then 70. So likewise, the file download will be having different ranges. So that is dynamic data flow. Okay. So that's why already we have seen that the synchronous data flow is mainly useful for digital signal processing applications, mainly for signal processing, because signal processing applications, most are frequency based. Frequency based are mostly are constant. But dynamic data flow, it's completely dynamic. That means for each and every firing, you can able to generate multiple number of tokens. Okay. So DDF have firing rules as well. So the second thing here is that this dynamic data flow have firing rules also. They have some rule. That means before I start, let me have a condition. So I can have a condition as well. Sorry. So before I start a rule, I will have a condition as well. So that means I'll check the condition. So that is a firing rule. So one good example for firing rule is once you seated on your car, let's say you are a driver, you are seated on your car. If you didn't wear the seat belt in the next 2 to 3 seconds, then automatically a beep, there will be a beep indicating that the seat alarm have been enabled and you have to fix the seat belt. But it will be reminding you for 2 to 3 times. After third time, it stopped. So that means before I start, it gives me a condition. So that is what firing rules. DDF might have firing rules. Okay. In SDF, actors produce fixed number of tokens. So again here in SDF, it produces fixed number of tokens on each output port. In DDF, the number of tokens can be varied, can be can be varied number of tokens. So first time it generates 2 tokens, second time it generates 5 tokens, third time it can generate again 4 tokens, again it comes to 3 tokens, then 11 tokens. So any number of varied number of tokens a DDF can generate, whereas static data flow can generate only fixed number of tokens. Okay, so that is on DDF. Then also the firing rules themselves need not be constant. Upon firing, a DDF actor may change the firing rules for the next firing. So first time the firing rule is different. For the second condition, the firing rule is different. One good example I'll just tell you. You wear the seat belt. So first time the firing rule is you wear the seat belt. So after the seat belt sign is off, that means once you wear the seat belt, now your door is not properly locked. The car door is not properly locked. Okay. Now in the first case, you didn't wear the seat belt, the door also not locked, but it has priority. First firing rule is it gives for seat belt. So seat belt is given. But after that, the door is not locked. Now the next beep will be for the doors. The next beep will be for the door. So that wise, second time when it is firing, the new firing rule have been in place. So likewise, when the car is running, it has a different firing rule. When the car is in stop mode, it's a different firing rule. So it's like that. Okay. So when you apply the brakes here, the lights will be switched off. When you release the brake, the lights will be on. Okay. So likewise, there are multiple firing rules available in DDF, and during each and every firing, the rules can also be changed. The token number of tokens can be varied. So all options are available in dynamic data flow. Okay. Now there's an example here. This example we will see in real time. We can see we'll adjust some parameters and then I can explain you also this example. Okay. Now DDF director. So far we have seen STF director. Now we are seeing DDF director. So DDF means dynamic data flow director. Okay. Now we have a ramp signal. Usually ramp means what happens is this is the ramp. This is the ramp. So ramp signal means it is like a x and y will be varying at a slope. Okay, so that is what the ramp signal usually. Now in the ramp signal, there is a Bernoulli's module. The Bernoulli's actor is generating true or false. The Bernoulli's actor is generating true or false in this circuit. Circuit. So we have a Boolean switch and we have a Boolean select. So we have two options: Boolean switch and Boolean select. Okay. Now the Boolean switch, it will be either true or false. The Bernoulli actor will throw randomly a stream of true or false. Okay. So let's say if a true comes. Okay. Now let me say if a true comes. Sorry. So there is a true here. When a true comes, the true will go here. So this is true here. When the true comes, the true will go here. Scale by -1. Scale by -1 means the true value will be multiplied by this minus. Then after that, the true comes here and plot in the sequence plotter. So that means whatever value we get the true value. True value means usually 1. True is 1. False means 0. When true 1 comes, 1 into -1 will be -1. So the -1 will be the negative axis. So negative axis means this axis will be the, so bottommost will be the true one. Okay, now you can see that this is the bottommost. So this is for true condition. This is for true condition. Okay. Now, if suppose the Bernoulli actor is producing false statements, if it is false, now false will be this thing. So it goes here. The scale will be 1. 1 means multiplied by 1. It usually will be zeros. So in that case, it goes to false statement, then the sequence here. Now this will be printed here. Okay. So since it is a ramp signal, so the ramp signal will be scaled by this value and it will be positive. Okay. But usually false means it is 0. So 0 will not be multiplied there. Only the ramp signal is being multiplied. So the ramp signal is multiplied, but it select either true or false. So true means it goes via the top cycle. False means it go via the bottom cycle. So for true, this will be executed. For false, this will be executed. So this will be the false line. This will be the false line. Now your waveform will be predicted like this. So you can see that there are two ramp. So one ramp in the top. So this area is false, and the bottommost ramp is for true. Okay, we'll see that we'll change this value also in the real example. We'll change the value. Okay, now we can see the example, the points, the Boolean switch and the Boolean select to accomplish conditional firing, the equivalent of if then else in an imperative programming language. So it is a simple logic of if then else. So generally in the looping statement, what we do is if condition, then true means this, false means it will go for a else statement. So true will be executed this and false will be executing this. Okay, usually we understand this is the concept. In the above figure, in this figure, the Bernoulli actor produces a random stream of Boolean value to tokens. So the Bernoulli actor produces a random stream of Boolean value. Boolean value means zeros or ones or true or false like that. True, false, false, false. Then true, false, true, false like that. In any order, it can able to produce. This control stream controls the routing of tokens produced by the ramp actor. So by the ramp actor, when Bernoulli produces true, the output of the ramp actor is multiplied by -1 using the scale factor. So the ramp actor value is multiplied by -1. That means not the true and false is multiplied. It's the true means the ramp factor will be multiplied by -1. False means multiplied by 1. Okay, as simple as that. False means multiplied by 1. True means multiplied by -1. Then it will be going and printing at the sequence plotter. So that is what happened here. When Bernoulli produces false, scale 2 is used, as we have seen. It passes its input through unchanged. The Boolean select uses the same control stream to select the appropriate scale out. Okay, there is a very simple logic. We will see this example, how this example worked out. But the same modified version of this, now the Boolean select is altered here. So instead of true and false, it is interchanged like false and true. Okay. Now what happens when the ramp value is coming here, the true value, when it goes true here, the ramp is multiplied by -1, but it goes and enters in the false. it goes and enter into Boolean select is there. So there is a false is being selected there. Earlier it was selecting true, it was fine, but now it is selecting false. That also we will see how the waveform changes here. Okay. Now in the case of false here, the ramp value will go to -1, then it goes to true. So false true, when the switch is false, then nothing will happen. When the switch is true, it ends up in the false statement. It end up the Boolean select as false. So during the time we have unbounded buffer. Unbounded buffer. So when multiple true streams are selected at the input, then there will be huge number of accumulation of false at the Boolean select. Because of that, there will be a bounded problem, unbounded problem. So buffer will be full or buffer will be full. So there will be unboundedness available on this particular thing. So in the same example, we will change. We will select how these things are happening. Okay. So this is an example number 2. Maybe you can check it here. In this case, the inputs to the Boolean select have been reversed. Unlike the earlier model, this model has no schedule that assumes bounded buffers. The Bernoulli actor is capable of producing an arbitrarily long sequence of true value tokens, during which an arbitrarily long sequence of tokens may build upon the input buffer for the false port of the Boolean select. So, because of the true value tokens, there will be huge number of false port on the Boolean select. That's a buffer, thus potentially overflowing the buffer. So that will be overflowing the buffer because those cannot be handled. Okay, now we can see in this case, see that the ramp is not here. Okay, so the curve seems to be curvy. There is no ramp here. In the bottom side also, you can see. So there is no ramp. Just wait 1 minute. Hello, ma'am. மேம் பாஸ்வேர்ட் ரீசெட் பண்ணிட்டேன். வெல்கம் @123 போட்டுக்கோங்க. டபிள்யூ மட்டும் கேப்ஸ் @123 மாத்திக்கோங்க பாஸ்வேர்டை. சரியாச்சா உங்களுக்கு? நான் இஷ்யூ சரியாச்சா? சரி இல்ல மேம், எனக்கு 1109 நான் செக் பண்ணி பார்த்துட்டு 109 பசங்களுக்கு சொல்லியிருக்கேன் மேம். வந்தனே நான் சொல்றேன். சில கிளாஸ்ல இருக்கேன் மேம். சரியா? முடிச்சு சொல்றேன். ஓகே மேம். Okay. Right. So the curve is not a ramp. So ramp curve means it should be like this, and similarly it should be like this, but it is not. So it seems to be curvy. So because of the unbounded buffer issues, this curve we are getting like this. Okay. Now this is what. So whenever the true tokens are coming, the false part of the Boolean select will have heavy amount of unboundedness will be there at the buffer. So the buffer overflow will be there. So first let me go with the dynamic data flow, then we'll go with the static data flow. So now what you do is, this is an example what we have seen now. Okay, so go to online. Once you click it, it goes to the corresponding website. Then right click, save link as. Okay, so you will get a file called as XML file, if then else. Save it. That is the first one. Again you go to the next one. This one, again you go online. Then you go like this, right click, save link as. You can see unbounded. Okay, unbounded. So if then else .xml and unbounded XML. Okay, right. So some people are asking, so where to download? So what you do is use Ptolemy 2. So if Ptolemy 2, then go to that homepage, Berkeley University homepage. Then you have, there are two versions. Development, don't go for development version. The development version, it's a new software. I mean, it's a very old software. Maybe some developmental activities are going on, but don't bother about it. Go with Ptolemy 2.11.0. Ptolemy 2 11.0. So Windows means you can download this. Mac OS means you can download this. Linux means you can download this source. So Linux means you have to build it. You have to build it in Linux. Windows means directly you can right click and then you can. But Mac OS, it's perfect. So today morning I gave a demo for the D1 slot students in Mac OS in my home. It was good. So no errors I got it. But in Windows also I got some error. In Linux also I got some error. But though the error is there, but still we could able to open the virgil.exe file. No issues in that. Okay, now Windows you can download maybe 300 to 500 MB software will can be downloaded, and then you can use the on-screen instruction. Okay, so anyway, I'll just open that now. Command prompt. So first let me go with the, but Windows it's too slow, but Linux, Mac it was very fast. So file, open file. I will go with if then else. Okay, so this PC downloads. If then else. Okay, so now this is the piece of software we have. Okay. Okay, now we can see DDF. Earlier we have SDF director. We have now PDF director. A number of iterations it is given as 40. We are not going to touch upon anything here. The ramp signal. So initialization 0. Step is 1. This also we are not going to change. Boolean switch it doesn't have anything else, and Boolean select also doesn't have anything else. So only two things is either true or false. So switching will be switching between true or false. Selecting means selecting true or false. Either of this it will take. So whenever true is there, the RAM signal will be multiplied by -1, and then the output will be given to true. Whenever it is false, the RAM will be given this path, and it will be printed on the positive axis. In the positive axis, and -1 will be printed on the negative axis. That's how it goes. Okay, and Bernoulli, it has a probability of 0.5. You can see that a true probability of 0.5 here. So below that we have 0.5. Okay, we'll change this value one by one. So now first what I do is I'll just run this example. So I'm getting this waveform, the red colored one. I'm getting this waveform. Okay, so okay, so this is a waveform what we got. Okay, now what I do is let me close this in the Bernoulli. I'll change it to 0.9. So 0.9 means what happens? True probability is 0.9 means, see, 10 times when I send stream true or false, so 9 times it will send a true, and 1 time it will send you false. That's what 0.9. 0.5 means if I'm sending 10 times, 5 times will be true, 5 times will be false, but the order will be any order, not 5 times true and 5 times false. It could be true, false, true, false, true, false, or true, true, false, 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 true, 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 like that. Okay, so I'm committing it now. Now when I run it, you can see now, you can see the sample here. So maximum time true is 0.9. So true is 0.9 and false only 2 times. See that the signal only twice comes in the false side. Okay, so that is sorry, yes, this is a false side. The top is a false side, and you can see the ramp is perfect ramp you are getting. The perfect ramp you are getting here in the bottom side. So bottom side is a true side because we are given 0.9. Now what I do is I'll make with 0.1 now. 0.1 means true probability 0.1 means true will be coming only 1 time and false will be for 10 times, 9 times when you are going for total samples are 10. So in that case, you can see here. So in this example also we have the perfect ramp. So you can see the perfect ramp here, and 1, 2, 3, 4, 5, 6, 7, 8, 9. So totally 9 times we have got the true, and many times we got the false because our probability is 0.1. True probability we are given as 0.1. Okay, so this is one example of the DDF on a perfect scale. So here what we able to do is every time when the firing happens, the condition can be either selected based on true or false. Okay, so that's what here the Boolean switch conditions happen. And Boolean select also, it select true or false accordingly. So whenever the true selected, it comes here, false is selected, it goes there. Okay, so this way I can able to plot it. Okay, that is on first one. Now let me open the second thing, unbounded. That will have a different thing, unbounded. Okay, so this unbounded, again we have Bernoulli's 0.5 here. Then here the Boolean select, whenever it is false, it given to true. Whenever it is true, it given to false. Okay, so that's how the way the Boolean. Now we can check the value. Now we can see this is how the way we got the output. Okay, so we can see the positive side and the negative side. You can see. So here we have given 0.5 here. Let me use 0.9 here. So when you use 0.9, you can see that the negative side nothing is there. So mostly they are zeros when I use 0.9. So even the previous case, the negative side was there, but now in this case it is not, and even it is not a perfect ramp. It's not a perfect ramp because 0.9 means true I am getting. So when the true is there, it goes to false. So that means most of the things are in the unbounded buffer. So that's what it means. So obviously it has to go to the negative side, but because of that, huge number of tokens are generated at the false side. So which makes the unbounded buffer there. So buffer will be overflown. Now the same case, I change it to 0.1 here. Commit. So when I try this, now this is what in 0.1 happens. So again in 0.1, in this side again we have all the buffer. So only one time will be true, all the time it will be false. So when the false is there, it goes to scale 2, then true. So that's how the way the false is projected. So the true is not projected. So you can see in the previous graph and this graph, the first one graph is consistency because both the sides we have negative as well as positive both the sides, but in one side it's only negative. So this time it's negative 0.1. 0.9 means on the one side. The other side doesn't happen anything. So because of the buffer at the input port of the Boolean select. Okay. So life means you should have happiness and sadness. Both should be there. High means low should be there. Positive means negative should be there. So everything have two sides. In the previous graph, we have both the sides. The perfect ramp we have. The whether positive or the negative side. But this time in this graph, it's completely upside down because of the unboundedness. Okay. So this is one example of this DDF director. So DDF means dynamic data flow. Okay. Now let me open some more graph which yesterday we have to try. Let me check. So the synchronous data transfer. See some graphs we have seen in the example, but I didn't show you. So did I show you this graph or this I already seen? We have already seen. Yeah, this graph. This have you seen it? This graph, students?
Yes, sir.
Yes, sir.
Yes, this you have seen. Yes, oh, audio. Okay, the microphone we have seen it. Okay, so this graph only. Okay, fine. This graph we didn't see. I will just show you now. So again, you go to online. The PDF book you can go to online. So right click, save link as. It will be maximum entropy spectrum. So already it's there. Anyway, I will take the maximum entropy here. Now let me open it. File, open maximum entropy. Okay. So this is the graph. So now all the three will be in the same sequence plotter in the right hand side. We have three waveforms: sine wave, 8000 sampling frequency. The frequency is 440 megahertz. That is first one. Second sinusoidal waveform, the frequency is 540 megahertz. Sorry, 540 hertz. The third sine wave is 2000 hertz. That is 2 megahertz. Okay. Then we have the Gaussian. So Gaussian, we have a standard deviation of noise power. So noise power is a standard deviation, and through the filter, it goes to the add signal. So add subtract box, all the signals are going to be added. And when it is added, it goes output of given into three waveforms. The same output is given to three waveforms. One is a spectrum, So the spectrum order is log to the number of inputs. So log 2 means log to the base 2 number of inputs. So number of inputs is how many inputs, accordingly the log 2. If 8 log 2 power 8 means totally 2 power 3 means 3. So I'll just write it down if you didn't understand it. Okay, so log 2 num inputs. So that means that suppose if 8 number of inputs is 8, then log to 8. Sorry, log base 2. Log to the base 2 8. So in that case, what happens? Your value will be log 2, then bracket 2 power 3. So 2 power 3. So that means you will get a formula of equal to 3 log 2 to the base 2. So then log 2 to the base 2 is 1. So your value will be 3 equal to 3. So that's what here the log 2 number of inputs. So that is what in the spectrum here. Now smooth periodogram. So smooth periodogram means the value is smooth, so that the curve will be smoother curve. Okay. So in that case, the value is 2 power log 2 number of inputs. The order is 8, 2 power log 2 inputs, the number of lags is 64. Then maximum entropy spectrum, the AR order. So I don't know what was said. So it's an AR order and 2 power log 2 number of inputs. The log 2 resolution is 8. Now you will get the same waveform in 3 different formats you can print. That's what it means. So because add subtract, you will get only one signal at the output, but the one signal is given into 3 spectrums, 3 different spectra to check how the waveform looks like. Okay, so this is again one of a STF director with a period, no period, nothing. So it's a constant buffer size. So you can see here. So this is the waveform here. Now we can see here the green color you can see. So the green color is a smooth one. So green color is maximum entropy. You can see here. So it comes like this and like this. The green color signal you can see. So this is the green color. So the blue and the red are they are not smoother. So that means they are just lines here. But the green color is a maximum entropy. It goes via the path. So it goes via the complete path of how a waveform can look like. Okay. So it gives a outline of the particular graph. Whereas the red is the periodogram and blue is a smooth curve. So when the periodogram says that heavy fluctuation, but the smooth curve is too simple to handle. But the entropy says that, okay, so what is the outline of the particular graph? Okay, so this is how the way usually scientists can predict the signal resolution. Okay, so yesterday we have shown an application on my voice through microphone, my whistling through microphone. Okay, the whistling says that it is a perfect sinusoidal waveform, but my voice says that it is completely different. Okay, so that is what the synchronous data flow graph. Okay, so this example only I thought of showing you yesterday. I could not able to do, and there is one more example in this book, and this example. So this is on a feedback with the SDF with a feedback. So the name of the output is sample delay. Okay, I'll just show you that as well. File open, sample delay. So file open, sample delay. So actually in the SDF initially when we see the example there was no feedback to loop, but when you add feedback, what happens? So the constant. So we have SDF director. So total number of iterations is 9. Totally 9 iterations. So vectorization factor starts at 1. So 1 to 9 it can print. So 9 up to 9 you can print. So the constant value is value starts at this 1. Firing count limit is none. No firing count. Then add subtract, it is added here. So the constant value is added along with the feedback value. So feedback from the sample delay factor also been added here. The sample delay factor says that it starts at 0. Okay, so that's 0, and the 0 is coming here and the constant value is coming here, and it will be adding and then printing. So the display will be there for printing. Now see the output. The output says that 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So totally up to 8. So total 9 firings. So it shows up to 8. Okay, so it shows up to 8, 0 to 8. Now when I check it, this delay I'll give it from 2 and commit. So when I do the commit, now when I run it, it says from 2 to 10. So again, totally 9 firings. So 1, 2, 3, 4, 5, 6, 7, 8, 9 firings totally. Now when I say the go to the director, you count up to 15 firings. Let's say 15 firings commit for the STF director, totally 15 firings. Now in that case, when you run it, it shows up to 2 to 16. 15 times it fires. Okay. So this is a simple synchronous data flow with a feedback loop. The feedback loop is probably through a sample delay. So the delay factor gives the feedback loop. So that means each time the value is printed will be with the value of a delay. So this example also, we have a feedback. The SDF model with a feedback loop must have at least one instance of the sample delay actor in it. So one instance should be there for enabling the feedback delay. Okay. So I think that's all on this distributed data flow, so dynamic data flow and synchronous data flow.